Hello. Today we are examining the effects of gravity and drag on the motion of a free-falling object for Lab 2. For this lab, we were to drop something that would fall relatively slower than a rock, so I chose a crumpled piece of paper because its non-uniform surface will have a greater drag force than that of a ball, so it will fall slower. I put the video of the falling paper into Tracker to extract position data, and from there created models for the falling paper with and without a drag force accounted for. A short summary of my results is that the model with no drag force overpredicts the final position of the paper, while the drag force model is very accurate for the final position. Both my models underpredict the position during the actual falling. We use similar concepts as the last lab, such as updating position with the position update equation and updating velocity with the momentum principle. In this lab, however, we will have a net force acting on the paper affecting its motion. The net force will be a sum of the gravitational force of the paper and the drag force on it in the air while falling. The equations for these forces are shown. The letter B in the drag force equation is the coefficient of drag for paper, which we fit to our data model and the model with the drag force. Main edits to the starter code were as follows. I inputted the formulas for the forces, which were multiplied by j hat, a unit vector, so that they were vector quantities. I had to input the equations for the position and velocity updates, and the starting position and velocity. I also had to adjust the arrow scale to show a big enough arrow for the forces. The B value was obtained through trial and error of trying to fit it to my data. The goal was to have a B value that made the last position of the model be as close to the actual final position from Tracker. As you can see, the gravity-only model overpredicts the final position, while the model with drag force is very similar to the actual value, mostly due to fitting the B value. Both underpredict the motion while the paper is falling, though. The model curves are also very similar, which I think is due to the B value being very small. Now we can look at the velocities of each of the models and the actual data. This analysis corroborates the position data because the models have slower velocities than the actual data during the fall, but then the actual velocity starts to flatten if we're looking at the general shape of the curve. This means that the actual paper is starting to reach its terminal velocity, which is effectively the max velocity. This is when the drag force equals the gravitational force so that there is no net force, making the velocity constant. The model with drag force also looks like it is starting to flatten to a lesser degree, so it is approaching the terminal velocity, but not there yet due to the B value being very small, so it takes longer for the drag force to equal the gravitational force. The gravity-only model will keep accelerating in the negative direction because it has no force counteracting it. If the paper was thrown downward initially, it would have a non-zero initial velocity. Regarding its terminal velocity, it would reach it quicker because the paper's velocity is already starting closer to that maximum. I justified this by testing an initial velocity of negative 3.5 meters per second in the model with drag force. As you can see, the curve for the position straightens into a straight line, meaning its slope is constant, meaning that its velocity is constant. Sources of error would be the actual drop of the paper ball, since it did roll off my finger and dropped at an angle. This could have skewed the data in some way since it wasn't falling straight down. There is also error in marking the positions in Tracker, because the frames were blurry at times, so it was hard to mark the exact center of mass. Lastly, the drag coefficient B is very small, likely due to some error in the tracking data, which leads to the terminal velocity and models not being as accurate as they could be.